Hi guys, in the last 3 lectures we have covered single phase, half wave, uncontrolled rectifier for R load, L load, RL load, RL with freewheeling diode, RE and RLE type of load. Okay, in this lecture we will start single phase half wave controlled rectifier and we will see the circuit for R load and L load in this lecture, that is lecture number 10A. Okay, so before moving into this lecture I would like to give you one important point, that is in all the previous 3 lecture, suppose you have to find the input power factor. We are putting input power P in is equal to P out. Okay, and P in is equal to P out, and input power is source RMS voltage, source RMS current cos phi is equal to P out, right? And for output power we have to see whether the load is voltage strip type of load or current strip type of load. Okay, now to find the source RMS current, you have to see whether the source RMS current are equal to the load RMS current or not. So take one point, that is in single phase half wave uncontrolled rectifier, the waveform of source current and output current, that is I naught, are same for all type of load except RL with freewheeling diode. This is the load in which source current is not equal to the load current. In this case RL with freewheeling diode, we are making load current, that is I naught, continuous. Okay, means even after turning off the diode we are getting load current, that is I naught. I naught is continuous, we are making I naught continuous by inserting freewheeling diode, but source current we are getting up to pi only. That's why source current and load current are not same in RL with freewheeling diode. For other type of load like R load, L load, RL load, RE load and RLE type of load, source current and I naught, that is load current, the waveform of source current and load current are same. That what do you mean by this? This means IS RMS must be equal to I naught RMS because their waveform are same. Also IS average must be equal to I naught average. This will help you in finding input power factor. Now let us move to the single phase half wave controlled rectifier. So first I am taking as a R load. The concept is same as the single phase half wave uncontrolled rectifier. Only what I am doing, I am replacing diode with thyristor. We know what is thyristor is. Thyristor is semi-controlled switch. Semi-controlled means the turning on of this switch is in our hand while turning off is not in our hand. It depends on the supply. So we are using thyristor in order to convert AC signal into DC signal. Let us see. We are having source voltage is equal to Vm sin omega t. The waveform of Vm sin omega t will look like this. Now in earlier case, means in single phase half wave uncontrolled rectifier, whenever this Vs is greater than 0, then diode starts conducting because it is uncontrolled switch. It depends upon the turning on and turning off depends upon the supply for diode, right? But here I am using thyristor, means no matter you are supplying Vs greater than 0, when you trigger the thyristor then only it will starts conducting. Means in order to turn on the thyristor we must give Vs greater than 0 and as well as we have to supply the gate current Ig not equal to 0. Whenever the thyristor is in forward blocking mode, then we have to trigger this thyristor in order to turn on the thyristor. So what I am doing, I am triggering this thyristor, I am giving this gate current at alpha. Let us say I am triggering this thyristor at an angle alpha. This is at an angle of alpha. Now I will divide like this from 0 to pi. First I will consider from 0 to alpha, then from alpha to pi. Okay, and alpha is nothing but triggering angle. See here, from 0 to pi supply voltage is positive, Vs is greater than 0, means this thyristor will be in forward blocking mode. So from 0 to alpha we are not triggering this thyristor, means in this case the thyristor will be in forward blocking mode. Is it fine? So from 0 to alpha the thyristor is not triggered by supplying gate pulse, means it will not conduct. So output voltage I will not get from 0 to alpha. So output voltage will be 0. Similarly output current also 0. Okay. Now at omega t is equal to alpha, I am triggering this thyristor. So whenever I will trigger this thyristor in forward blocking mode, then it will move to the forward conducting mode. Okay, so it will move to the forward conducting mode, means this thyristor will start conducting and I can replace this thyristor by short circuit. So output voltage what I will get, if I will replace this thyristor by short circuit from alpha to pi, then output voltage will follow the input voltage. Apply KVL here. So V naught is equal to Vs is equal to Vm sin omega t, and I will get I naught is equal to V naught by R. Okay, so from alpha to pi, this is alpha and this is pi, the thyristor will conduct and output voltage will follow the input voltage like this. See, output voltage is following the input voltage like this. Now what will happen after pi? After pi, the supply voltage is getting reversed, means from pi to 2 pi, supply voltage is getting reversed, means Vs is less than 0. The moment when Vs supply voltage is less than 0, means this thyristor will move into the reverse blocking mode, means this thyristor will replaced by open circuited, and in this case V naught will be 0, I naught is equal to 0, and what will be the voltage across thyristor? The voltage across thyristor, apply KVL here, the voltage across thyristor you will get Vs minus V naught, Vs minus V naught, and we know that V naught will be 0 because it is open circuited, so output current will be 0, hence V naught is equal to output current into R, so V naught will be 0. So what is the voltage across thyristor? The voltage across thyristor will be Vs only in this case. So from pi to 2 pi, the thyristor will go into the reverse blocking mode and we are not getting output voltage, output current, and voltage across thyristor is equal to supply voltage. So see here, from pi to 2 pi, this is 2 pi, output voltage 0. Similarly, output current is 0, as we know that it is voltage steep type of load. So output voltage waveform and output current waveform are similar. Now what will be the voltage across thyristor? So the voltage across thyristor will be equal to the supply voltage from pi to 2 pi. See, from pi to, this is 2 pi, right? I think there is wrong in this waveform. The waveform will look like this. From pi to, this is 2 pi, right? So from pi to 2 pi, the voltage across thyristor Vt will follow the Vs, that is equal to Vs. So waveform will somehow look like this. It will follow Vs like this, and again after that it will move into the forward blocking mode like this. Okay, this is 2 pi plus alpha. So the voltage across thyristor will follow the supply voltage from pi to 2 pi, and it will continue to follow after 2 pi also, unless and until we are giving the next firing angle. When we will give the next firing angle, then only it will starts conducting, otherwise it won't conduct. Okay, so if I will have to find the peak inverse voltage of thyristor, then we can easily say that the peak inverse voltage of this thyristor is Vm. And if I will have to find the circuit turn of time, I defined the circuit turn of time in previous lecture, that is the time for which the power electronic devices is in reverse bias. Okay, so in this case the thyristor is reverse bias from pi to 2 pi only. See here also you are getting voltage, that is the forward blocking voltage, and from 2 pi to 2 pi plus alpha also you are getting the voltage across thyristor, but that is not in reverse bias condition, that is the forward blocking voltage. But to find that circuit turn of time, you have to see for what angle the thyristor is in reverse bias. So this thyristor is reversed bias for angle pi. See, it is reversed bias from pi to 2 pi. So this will be the circuit turn of time. This is omega Tc, that is equal to pi. So Tc will come out to be pi by omega, where omega is the input frequency. Got it? Now take note. So first note is we have to find the average output voltage. So what will be the V naught average? V naught average I can easily calculate by this waveform. See, this waveform has a period of 2 pi. So 1 upon 2 pi, from where it is conducting from alpha to pi. So it will be alpha to pi, and it is following the Vm sin omega t, that is supply voltage. So Vm sin omega t. Solve this integration, you will get Vm upon 2 pi into 1 plus cos alpha. Okay, you can clearly see here that the output voltage is depending upon the firing angle, that is the cos alpha. Okay, if alpha will be more, then output voltage will be less. If alpha will be less, then output voltage will be more. That's why it is known as controlled rectifier, means we can control the output voltage by varying firing angle of thyristor. Got it? So if I will put alpha is equal to 0, then I will get output voltage V naught average is equal to Vm upon 2 pi. That is nothing but output voltage of single phase half wave uncontrolled rectifier for R load. Okay, so whatever the formula we are going to derive in single phase control rectifier, that formula is valid for single phase half wave uncontrolled rectifier also. Only you have to put the alpha is equal to 0. Okay, now the second point is what will be the I naught average. The I naught average, I will get V naught average upon R. Since this is a voltage stiff type of load, so waveform of I naught and V naught are similar, so we can find like this. Third point is V naught RMS. V naught RMS, we are finding V naught RMS we can find by using this waveform, output voltage waveform, that is equal to under root of what is the time period, 1 upon 2 pi, from where to where I am getting output voltage, alpha to pi, and this is Vm sine omega t square into d omega t. Okay, after solving this equation you will get 1 upon 2 pi, take Vm square outside, alpha to pi, and sine square omega t can be written as 1 minus cos 2 omega t by 2. Okay, so after solving the above equation I will get V naught RMS is equal to Vm by 2 into 1 upon pi into pi minus alpha plus sine 2 alpha by 2 ka under root. This is 1 by 2. Okay, fourth point is you have to find the output power. So output power I can easily find since it is a voltage stiff type of load. So output power for R load is nothing but V output RMS voltage ka square by R, or you can see that I naught RMS square into R. Now the fifth point is input power factor. So for finding the input power factor, I told you that you put P in is equal to P out, and we know that P in is Vs Is cos phi is equal to P out, that is equal to IOR square into R. Okay, and we know that the source current and the output current waveform are same for half wave control rectifier considering R load. Okay, so Is is equal to IR here. So finally cos phi will come out to be IOR into R by Vs. Okay, you can also write RMS output voltage VOR upon Vs. Now the sixth point is conduction angle of thyristor, that is gamma of thyristor. This is known as conduction angle of thyristor. So I told you earlier what is the definition of conduction angle. For what angle the thyristor is conducting, that is known as conduction angle of thyristor. See here, the thyristor is conducting from alpha to pi. So what is the conduction angle of thyristor? The conduction angle of thyristor will be pi minus alpha. Seventh point is beta. What is the extension angle? Up to extension angle what is defined as up to what angle the thyristor is conducting. So extension angle of thyristor, beta of thyristor is coming out to be up to what angle it is conducting? It is conducting up to pi. See, current I am getting up to pi only in one cycle. So extension angle is coming out to be pi. Now the eighth point is what is the peak inverse voltage? We already derived peak inverse voltage is equal to Vm. And ninth point is what is the circuit turn of time? This is also we have derived, that is equal to pi by omega. Now we will move to L type of load. Same circuit, only the load is replaced by purely inductive. So here also in place of diode I replace the diode with thyristor, means it is a control rectifier having purely inductive load. Now let us suppose this thyristor is triggered at an angle of alpha. Okay, this thyristor is triggered at an angle of alpha, means this thyristor will start conducting, means it can be replaced by short circuit. So the moment when you will replace this thyristor by short circuit, then I can apply KVL. I will get V naught is equal to Vs, that is equal to Vm sin omega t. Okay, and V naught can be replaced by L di by dt is equal to Vm sin omega t. Is it fine? So di will be Vm upon L sin omega t dt. Now integrate this from 0 to I, and here at what angle I am triggering? I am triggering from alpha to, let us say I don't know the extension angle, so let us say up to omega t. So I will come out to be Vm upon omega L cos alpha minus cos omega t. Okay, let us suppose the current I am getting up to extension angle beta. So to find extension angle beta, what I will do? I will put omega t is equal to beta, and we know that at beta the current is going to be 0. Extension angle is up to what angle it is conducting, means at omega t is equal to beta the I must be equal to 0. So I will get, put I is equal to 0 here, omega t is equal to beta, you will get cos alpha is equal to cos beta. What do you mean by this? Beta will come out to be 2 pi minus alpha. So I know the extension angle, means up to what angle it is conducting, and from where it is conducting from alpha. This is the waveform single phase half wave uncontrolled rectifier with purely L load. Now I am making this waveform for controlled rectifier. Suppose I am triggering this thyristor at an angle of alpha. Let us say this is the angle alpha. Okay, this is alpha. So I am triggering the wave this thyristor at an angle of alpha, means after alpha the output voltage will follow the input voltage. So output voltage will come out to be after alpha like this. Okay, and it will follow the input voltage up to that point at which thyristor is conducting, and we know that the thyristor is conducting from alpha to beta. Let us say alpha is somehow here, the alpha is here. So I will get current from here only. I will not get current from 0. I will get current from alpha like this. Okay, and it will starts conducting till beta, where beta is equal to 2 pi minus alpha. So the current waveform I will get like this. Got it? This is the waveform. The waveform shown in black is for L load in uncontrolled rectifier. So don't get confused. Okay, it is starts conducting from alpha and it will conduct till beta, that is equal to 2 pi minus alpha. This is 2 pi. So what will be the conduction angle of thyristor? The conduction angle of thyristor will come out to be gamma of t is equal to beta minus alpha. So put beta is equal to 2 pi minus alpha, you will get 2 pi minus 2 alpha. Okay, so average voltage across inductor we know that is always 0. Remember this, VL average voltage across inductor is always 0 in any case. Okay, so whatever the positive voltage I will get, that must be subtracted in negative voltage. Also we can say that V naught is equal to Vs only when this thyristor is conducting, and this thyristor is conducting from alpha to beta. So I will get output voltage from alpha to beta like this. This is beta. So I will get output voltage only from alpha to beta. I won't get from 0 to alpha, and then again from beta to 2 pi I won't get. Okay, in this way the cycle repeats. So output voltage I am getting from alpha to beta, and that is equal to input voltage, and current I am getting from alpha to beta like this, where maximum current I will get at omega t is equal to pi. This is the I max, and I max we can easily find by putting omega t is equal to pi in this equation. Got it? So take one note. First note is, what is the current equation I am getting? I naught t I am getting is equal to Vm upon omega L cos alpha minus cos beta. Okay, where beta is equal to 2 pi minus alpha. Okay, third one is the conduction angle of thyristor. Conduction angle of thyristor is beta minus alpha, that is equal to 2 pi minus alpha, that is equal to 2 pi minus 2 alpha. Fourth is circuit turn of time. So for finding the circuit turn of time, we have to see the up to what angle the thyristor is reverse bias. See here, up to beta the thyristor is conducting. After that it will get open circuited, and the voltage across thyristor is nothing but I will get Vs, supply voltage, source voltage. The voltage across thyristor will follow the supply voltage like this. So for this period the thyristor is reverse bias. You can see clearly that the supply voltage is equal to thyristor voltage I will get only when this thyristor is not conducting, and this thyristor is not conducting after beta. So after beta the supply the voltage across thyristor will be negative, and it will be negative up to 2 pi. Okay, so the circuit turn of time will come out to be, so this will be 2 pi minus beta upon omega. Okay, See it here also from 0 to alpha it is also not conducting, but in this case if you will find the voltage across thyristor, then you will get in first quadrant like this. The voltage across thyristor will be somehow like this, and it will continue till 2 pi plus alpha. But this is the forward blocking mode, not reverse blocking mode. Circuit turn off time is defined as for what angle the thyristor is in reverse bias. Here from 0 to alpha the thyristor is not in reverse bias. So I will not include this. The thyristor is reverse bias only from beta to 2 pi. So circuit turn off time will be 2 pi minus beta upon omega. So that's all about this lecture. In the next lecture we will cover RL load with RL with freewheeling diode. That is the lecture number 10B. So if you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving you can join our Facebook group. Thanks for watching this video.